Alright, so this is chapter 6, Dynamics 1, motion along a line. Later on we'll have Dynamics 2, motion along a plane. So this is just one-dimensional motion. So here are the learning objectives. We're going to draw and make effective use of force diagrams. So we learned last chapter how to do the force diagrams, how to draw them. Now we're going to use them. We're going to recognize and solve simple equilibrium problems. We'll distinguish between mass, weight, and gravity. We'll learn and use simple models of friction and drag. We already did some of that last chapter. Here's the important thing. We're going to apply the full strategy for force and motion problems to problems in single particle dynamics. So basically, what we're going to do in this chapter, we're going to we're going to use everything we've learned up to this point, which is kind of a blessing because if you don't feel real comfortable with some of the material we've gone over, this is going to be a nice opportunity to use it and to maybe learn it better. All right. So this is a great chapter because, again, use everything that we've studied up to this point. All right, so here's a question. An object is in equilibrium. Therefore, so pause your video and figure out the answer. And I'll give you a hint. There's 2 correct answers. All right, what is equilibrium? We talked about this last chapter. Equilibrium just means that the sum of the forces equals 0. Well, that means MA equals 0. So that means that A equals 0. That means that dV dt equals 0, right? So it just basically means that the velocity is not changing. So, okay, the velocity is not changing. So it could be moving, right? Constant velocity, or it could be at rest. Now, so make sure you understand these words. If it's at rest, that's called static equilibrium. If it's moving, it's called kinetic, because kinetic means moving equilibrium. Right? So equilibrium just means that the sum of the forces equals 0. So there's no acceleration, so nothing is changing. So how do we solve equilibrium problems? Just like this. Right? I mean, that's really how you do it, but I mean, that's totally true, but sort of useless. What we really do is we're going to break everything up into x forces, y forces, and we're probably, I mean, you could z forces, but we don't usually have z forces. So this is true, but in practice, what we're going to do is we're going to say that the sum of the x forces equals 0, and the sum of the y forces equals 0. And so you can imagine it's going to be a lot of trigonometry and things like that, but that's okay. All right. Now, so if equilibrium says this, what does non-equilibrium say? Well, that's sort of obvious, right? So non-equilibrium says this, right? So what is it? So non-equilibrium says that the sum of the forces equals MA. No kidding, right? No kidding. So how do you solve a non-equilibrium force problem? Well, you just say that the sum of the x forces equals MAX, and the sum of the y forces equals MA sub y. That's all. So, you know, we're going to be resolving lots of vectors and components and things like that, which we've already discussed in gory detail. Okay. So here's a simple problem. I just want to go through it to show you the method. Okay, a 100-kilogram block hangs on a rope. Find the tension in the rope if the block is stationary. Okay. Draw the force diagram. So as we saw last chapter, what are the forces acting? Okay, what's the object? Sorry, what's the object? The block. 100-kilogram block. So what are the forces acting on that block? Well, there's tension and there's gravity. So that's it. Or there's nothing else, right? There isn't a normal force because there's no surface. All right, so you just draw the picture. The force diagram. So there's the tension and there's the weight, which which equals mg. Now, it says the block is stationary. Well, that's good, right? So if it's stationary, it's not accelerating. So this is an equilibrium problem. So we say that the sum of the forces in the y direction equals 0. Okay, well, what is it? Well, and we're using Randy 9 coordinate system, might as well. So t is up, weight is down, right, and equals 0. So therefore, the tension equals the weight. That's all there is to it. And the weight is equal to mg. The mass is 100 kilograms. G is 9.8 meters per second squared. So that's 980 newtons. So that's the answer. 980 newtons. All right, so again, what are the steps? Determine the object. Determine the forces. Draw the force diagram. Ask yourself, equilibrium or non-equilibrium? If it's equilibrium, sum of the forces equals 0. If it's non-equilibrium, sum of the forces equals ma. And then just do what the problem asks. Okay. All right, now, this is the problem. I want you to do this. So the only thing is different. So I did, the block is stationary. Now I want you to do this. The block is moving upward at a steady speed of 5 meters per second. So pause your video and do it, please. All right, I assume you've done it. You know how I always say you should underline or circle the important words? Well, here's an important word, right? Steady. It's moving at a steady speed. So that means that the velocity is not changing. That means that the acceleration is 0. That means it's an equilibrium problem. So this answers that question, right? Because if it's stationary, the acceleration is 0. If it's moving upward at a steady speed of 5 meters per second, the acceleration is 0. So this is the answer to this problem as well. Same solution. Okay, that was nice. Didn't have to do any work. All right, now I want you to do a little bit of work. Okay, so now the block is accelerating upward at 5 meters per second squared. So please pause your video and work out the problem. All right, I assume you've done it. I hope you've done it. So now it's accelerating. So it's a non-equilibrium problem. So what I suggest what you do when you draw your force diagram, just draw your acceleration vector. It just helps your brain remember equilibrium or non-equilibrium. Okay, it's non-equilibrium, it's in the y dimension, so we just have the sum of the y forces equals ma sub y. Right? All right, so what do we have? Positive t, negative mg, and that equals, I already wrote it, right? That equals ma. Okay? Now we would find that, okay, so there we go. So this is really what we are interested in, this part right here. So we want to solve for the tension, so we have to put the mg on this side. So we have ma sub y plus mg equals tension. Now, just to save us a little work, we can back out the m. It's just a good idea. A sub y plus g equals tension. And then you just plug in the numbers. So the mass is 100 kilograms. Acceleration in the y direction is positive. That's why it's good to draw this thing so you don't get confused, right? 5 meters per second squared. And g is positive 9.8 meters per second squared. And that comes out to be 1480. going to be much more complicated than this later on, but this is just to show you how these problems are done. By the way, generally speaking, when you have a problem like this, when you have a force problem, right? You have to do a force diagram. Usually what you're after is the acceleration. And then you're going to use that acceleration in the associated kinematics problem. So that's why we're doing this, okay? In other words, you're going to have this kinematics problem, so we have to draw the pictorial representation, all that stuff, right? And then you realize I can't use any of the kinematic equations because I don't know the acceleration. So you're stuck. But then you realize, I can do the force diagram and solve for the acceleration using the force diagram, and then I can do my kinematics problem. So you kind of just imagine that the problems in chapter 6 are going to be long. So just, expect that. Okay, now we're going to just pause for a minute, and we're going to talk about mass, weight, and gravity. So here's a question for you. Does your mass change when you travel from the Earth to the moon? Your mass. Of course not. Why? Well, because, when you're thinking of mass, you're thinking of, how much matter makes up your body, right? And when you travel from the Earth to the moon, hopefully you're not losing an arm or a leg or something like that, So the mass is constant. Mass is constant. It's a property of the object. How about this, though? Does your weight change when you travel from the Earth to the moon? Well, yeah. Why is that? Because weight is mass times acceleration due to gravity. And on Earth, G is 9.8 meters per second squared. That's Earth. But on the moon, it's approximately equal to 9.8 meters per second squared divided by 6. So, very different, right? So, you can imagine, let's just pretend that you could go to the moon and you don't need one of these big, heavy spacesuits. So what would you do if you got to the moon? Well, what I would do, I would see how far I could jump, see how high I could jump, set the world record in the high jump, set the world record in the long jump, pole vault. It'd be a riot. Because you wouldn't weigh so much. All right. This is called Newton's law of gravity. So, Fg, force of gravity, and this is just between the Earth and the moon. It works for any two massive objects. So the force of gravity between Earth and moon, okay, uppercase G is just what's called the gravitational constant. It's this. You see it's pretty small, right? 10 minus 11. All right, so uppercase G is a constant. Then there's the mass of the Earth. There's the mass of the moon. And divided by the distance squared. Now notice the distance squared is the center. We'll talk about this in more detail later, but the center of the moon to the center of the Earth. Okay? And it's gravity, so it's attractive. So the Earth attracts the moon attracts the Earth, right? Okay. So here's a question using that. Okay, here's the question. So what's the force of gravity between you and the Earth? All right, so here's the Earth. Here's you. The distance between the center of you and the center of the Earth is basically the radius of the Earth, right? Right? Okay, so let's do it. So the force of gravity between you and the Earth is uppercase G. Mass of the Earth, mass of you, and again, the distance between the center of the Earth and the center of you is basically the radius of the Earth, squared. Now, wait a second. What else does, this is true, but we have a simpler way to write it. What's the force of gravity between you and the Earth? It's your weight. And what's the equation for your weight? It's just the mass of you Same for the last little bit, right? So therefore, what is lowercase g? Well, get rid of that. Okay, so what can we cancel? We can cancel the mass of u. Yeah, so that right there. So that equation right there is g, right? So lowercase g is the gravitational constant times the mass of the Earth divided by the radius of the Earth's square. And that's 9.8 meters per second squared. Okay? So there you go. All right. So in the United States, it seems that many people are constantly trying to lose weight. And so you have this organization called Weight Watchers and so forth and so on. But what are we really trying to lose? Mass or weight? Mass, right? I mean, if you want to lose weight, just go to the moon, right? But would you look any different? No, right? So you're really trying to lose mass. So Weight Watchers is a rotten term. They should be calling themselves Mass Watchers. But that doesn't sound very good, right? So, okay? So there you go. All right. So that's important that you know the difference between mass, weight, you know. And we'll talk more about this law of gravity later on. Like I said a couple of minutes ago, it works for any massive objects. So planets, potatoes, whatever. All right. Now what we want to do, we want to do some force problems. We're not going to do kinematics yet. We're just going to do the force problems. You remember last chapter we had some force problems and all you did is draw the force diagrams? Well, now we're going to solve those problems. So I hope you kept your diagrams. All right. So we did this the other day, remember? Okay, so here we go. So this is over the jet. Okay, so you should still have your force diagram. So I'm going to draw it. So that's the horizontal. All right, that's the angle. The incline is 30 degrees. So here's the plane, the jet. And what are the forces on the jet? So we had the thrust, and we had the lift, and we had the weight, and we had the air resistance, right? The drag. Okay, so you know this is a constant speed, straight line, so this is equilibrium, right? But anyway, so first of all, what are we going to do? What kind of coordinate system are we going to use? We're going to tilt it. We have to be crazy not to tilt it. So we're going to tilt the coordinate system. So this is our So this is our y-axis. Draw a straight line instead of a line. This is our x-axis. Okay. So that's the first thing we do. All right, we choose our coordinate system, we tilt it, and we draw the force diagram. Okay, now so this is the only one that this is the only force we have to resolve. That's kind of nice, right? And let me just call this theta. I'll put in a 30 later. And hopefully you remember that the incline angle is the angle between the weight vector and the y-axis. Hope you better remember that, right? Okay, so we got to resolve the vectors are all along the coordinate axes. So this is the adjacent, so this is W cos theta, and this is the opposite, so it's W sine theta. Okay. Is this equilibrium or not equilibrium? Constant speed, straight line, equilibrium. So we just have to do this. Okay, here we go. So the sum of the x forces. First of all, it's 0 because it's equilibrium. But what is the sum of the x forces? Okay, let's see. So we have t positive that way. We have r that way, so it's negative. And but we also have this guy, right? Don't forget this. That's going in the negative direction. So that's W sine theta. Minus W sine theta. And that equals 0. All right, let's actually plug in the numbers. Let's see. Okay, so we're trying to we're trying to find R. Let's solve for R, right? So here's the equation. So solve for R, so just put R to the left. So we have R equals T minus W sine theta. So T, where's T? 103. And the weight is what? 86,500. Times the sine of 30. And hopefully I did this right. I get 59.75. Okay, so there's R. So all we use is the sum of the x forces. That one, that one, that one. Now we want to find L, so that's the y. So the sum of the y forces, again, it's equilibrium, right? It's not going like this. It's not accelerating in this, in the y dimension. All right, so what are the y forces? L is positive. Negative, all we have is W cosine theta, right here. That was W cosine theta. L minus W cosine theta. Well, that's awesome. So that just means L. So therefore, L equals W cosine theta, which is the weight, 86,500 times cosine of 30. And hopefully I get that right. 74911 newtons. So that's all there is to it. Okay. So let's review. Choose a coordinate system, straight up or tilted. Draw the force diagram, which you better know how to do by now. Resolve the vectors that are along the coordinate axis. Typically when you have an incline, you're always going to be resolving the weight vector, because the weight vector is always straight down. So let's just get used to it, right? And then you have to ask yourself this question: is it equilibrium or is it non-equilibrium? If it's equilibrium, sum of the force equals 0. Non-equilibrium, sum of the force equals ma. And you just have an x equation and a y equation. X equation and a y equation. And you just do the math. That's really all there is to it. Okay. Not so bad, right? Right. Let's do this one. Okay, this is example 3. I guess I'm going to do this too, huh? I want you to do something for this. All right, let's do this one. Oh yeah, this is kind of a cool one. The question I did before, I call it a robot problem, because you just follow the steps and you just do it. It's not really exciting, You don't have to really do a whole lot of thinking. You just follow the procedure and you're done. This one, you'll see, you have to actually do some thinking. It's kind of fun. Okay, 1,000 kilogram steel beam is supported by 2 ropes. Each rope has a maximum sustained tension of 6,000 newtons. That means if the force is greater than 6,000 newtons, it breaks. Does either rope break? If so, which ones? Draw the force diagram. Use Newton's law of motion to solve the problem. Be sure to answer both questions. What do you mean both questions? Well, does either rope break? Yes or no? If so, which one or ones? All right? So this is kind of, like I said, this is kind of a cool question. And again, there's no kinematics, right? This is just a force problem. Okay, step 1. Force diagram. Now look, there's no incline, so we don't have to tilt the coordinate system or anything like that. So here we go. So just Randy Knight. All right, what are the forces? Well, this is the beam is the object. So there's gravity down, tension this way, tension that way. That's it. And there's two ropes, right? Okay. So you got to label them, you know, like T1 and T2. All right, so gravity. So there's the weight, which equals mg, and there's so okay, and mg. Well, we'll just leave it at that. And it's 1,000 kilograms times 9.8 meters per second squared. It's 9,800 newtons. I usually do that at the end. I don't know why I didn't now. Who cares? All right, then there's tension here. And okay, now look, if this is 30, this is 60, right? Because this is 90. So I don't know, for whatever reason, I decided to use this, not that. It doesn't really matter. You can use either one, it just doesn't matter. So that's 60 degrees, and I call that, can you read it? T2. So that's T2, right? Because row 2, yeah. So we're going to have to resolve this vector. So there's the x piece, so that's T2x, and this is the y piece, T2y. We have the rope number 1, so that's T1, and that's 80, right? I mean, what did I just say? 70. So if this is 20, that's 70. So here's T1x, and that's T1y. Okay. So let's do the x. Oh wow, this is kind of a mess. Woo. Okay. So let's do the x part first. Okay. So the sum of the x forces. Now let's see now. I mean, is it accelerating this way? No. I mean, it's at rest, right? So the sum of the x forces is 0. And what's the sum of the x forces? We have T2x. So what's T2x? It's T2 cosine 60. Right? T2x is T2 cosine 60. And then minus is T1x, which is T1 cosine 70. And minus, because it's that way, T1 cosine 70 degrees. All right, now you look at that and you say, ah, rats. Because two variables, right? One equation, two variables. You can't solve it, right? If you have two variables, you need two equations. And you know, I mean, you kind of expected that, right? Because we have we have an x problem, we have a y problem. So now we do the y problem. Okay, so the sum of the y forces, again, it's 0 because it's not accelerating. So what are the y forces? Well, it doesn't matter the order. T1y, right? And T1y is T1 sine 70. So we have T1 sine 70. And we have T2y, which is T2 sine 60, plus T2 sine 60. Don't forget the weight, right? Minus the weight, right? Minus the weight, which is 9,800. Minus 9,800 newtons. And that equals 0. Okay, so two equations, two unknowns. You can solve it whatever method you want. I think I used a substitution method this time. Sometimes I do, sometimes I don't. So use this, right? Use that and solve for T2. So T2 is equal to T1 cos 70 divided by cos 60. And that comes out to be 0.684 T1. Okay, so now we know what T2 is, right? Now we know what T2 is. So now let's plug in our value for T2 in this. Okay. And I'm going to plug in sine of 70 and sine of 60. Okay. Oh, I guess I'm not. First I'll write it out. Okay. So plug it in here. So we have T1 sine 70 plus T2. T2 is this plus 0.684 T1 sine 60 minus 9,800 newtons equals 0, right? Just plug it in there. Okay? So now we're going to solve for T1, right? We want to know what T1 is. So let's put this on the other side. Okay? Then let's solve for let's factor out the T1. So we have T1 sine 70 plus 0.684 sine 60 equals 9,800. And then you just divide by this. You do the same thing over here. All right. So that cancels, and then you get. I promise you get T1 equals 6,397 newtons. Okay. And then you get T2. So T2 is just 0.684 times T1. So you plug that in, and T2 comes out to be 4,375 newtons. All right. So if you're a robot, you stop right here. Hopefully you're not a robot, you're a physics student. So now you have to read the question or look at the question again and think about it. Okay. All right. Now it says that each rope has a maximum sustained tension of 6,000 newtons. Well, T1 is greater than 6,000 newtons, right? So what's going to happen to rope number 1? Rope number 1 is going to break, right? Okay, so rope number 1 breaks. So therefore, rope number 1 is out of the picture. So therefore, the entire weight of the beam is now held by rope 2, right? Okay, so what's the weight of the beam? We did that somewhere right here, 9,800 newtons, correct? So therefore, what's the tension? So what's the, without rope 1, what's the tension on rope 2? 9,800 newtons. Well, is that bigger than 6,000? Yeah. So what's going to happen to rope 2? It's going to break also. All right? So both ropes break. Okay, so this is kind of a good question, right? I can imagine this being like a multiple choice question on an exam, right? And they'll have this and they'll have this. And the robot people in the class, which hopefully we don't have any, they'll see this and they'll just mark it and they'll get it wrong because they didn't answer the questions. So that's what I mean. You gotta read the questions and answer the questions, right? Okay, so hopefully you understand that. Okay, let's quit.